Hi everyone and welcome to Chem class. Today I want to show you in detail what is happening in the substitution reaction when an alkane is reacted to form a chloroalkane. This particular example is a common one. We're starting off with ethane, reacted it with some Cl2 gas, and we're told that it requires a catalyst such as UV light that will enable this substitution reaction to occur. There's a little bit more detail to what's going on here, so I just want to explain that to you. The UV light attacks the covalent bond within the chlorine molecule. So it actually is attacking that particular molecule, not both of them together. And what happens to the chlorine molecule, as you might remember, that covalent bond is formed because the chlorine atoms each bring to the party 7 valence electrons. They need to share the energy of one more electron, so they're each sharing an electron from the other atom, so it's essentially a pair of electrons being shared, and we show that as a single bond. So when that bond is broken, we create 2 chlorine atoms that take back each of their 7 valence electrons. Now, ordinarily when we show electron dot diagrams, we show the 7 valence electrons, but what I'm going to show you now is a different way of representing this particular species, and this is now called a free radical. A free radical that's taken back its initial valence electrons, but out of its initial valence electrons, it is left with an unpaired electron. Notice how I've represented these particular species. The chlorine atom with one dot there represents one unpaired electron. So of the 7 valence electrons that it has originally, 6 of them are in pairs, and they're not the problematic ones. It's that 7th electron that is no longer paired to anything that makes this species incredibly unstable, and hence the name free radical. It's these unstable species that then attack and break the covalent bonds within the ethane. Once those bonds are broken, of course, we now have unpaired electrons, and the molecule will pair up with anything else that's available. So ultimately, we end up with a substitution of the chlorine. Let's do that in another color so we can show that clearly. The chlorine substitutes in wherever it has broken a covalent bond, and we end up with a byproduct, which would be the hydrogen that's been substituted, and there's also these other chlorines that are going to be floating around looking to share some electrons with something, so we end up with some HCl. This is oversimplified. This is showing you the particular pathway to make what we know is our desired product, as I said, super useful molecule. The reason I say it's oversimplified is in this we have all of these free radicals that have been created from all these Cl2 molecules that have been broken. So with all these free radicals, it's actually a crazy mess that we have going on because we can't control which bonds those chlorines are actually going to break. So in this mixture, although we have the desired product of a chloroethane, there's also going to be some dichloroethanes, and there's 2 isomers of that. You could have some trichloroethanes. You get the picture. We have continuous reacting of these free radicals impacting on this molecule and substituting in its place. What we look at in these pathways is the molecule that we are hoping to make, so the desired product, and we're just showing how that process occurs. But we do need to understand that there's a lot more going on. And that, of course, is why we also in this topic need to understand percentage yield, because percentage yield is where we get an appreciation for the fact that not everything reacts to 100% extent as we would expect and hope it to. The desired product is only going to be a percentage of that mixture. Hope that helps.